Session before lunch and the vision talks of the afternoon. Our first speaker in the session is Veronika Hubeny.
I would like to start by thanking the organizers for inviting me to present here and organizing this great conference. So this is about work in collaboration with Mukund Rangamani and Max Rota. I have bolded Max's name because he has been really the driver of this whole program. And it's an ongoing work. We initiated the sort of setup in these two papers, but it's a whole program that's very much in progress, and various people have now joined us. So the context of the talk is holography. In particular, the strongly coupled large central charge corner of the parameter space of ADS-CFT, which describes a classical bulk geometry. And the underlying motivation comes from the desire to understand how gravity or dynamical spacetime emerges from the dual non-gravitational description. So, recently we have had many hints and developments that suggest that entanglement structure plays a crucial role. And so the more immediate goal is to understand or characterize aspects of entanglement structure that correspond to geometric states, by which I mean states in a holographic CFT which describe a classical bulk geometry. And, entanglement entropy has been a much used and convenient quantity in this context. And so a completely separate motivation is sort of from the quantum information perspective to understand the information quantities derived from entanglement entropy. Now, of course, the usual definition of entanglement entropy, namely as the von Neumann entropy of a reduced density matrix pertaining to a given subsystem, assumes this factorization of a Hilbert space, which is absent in a quantum field theory. But this is now, it is now understood how to sort of get around that, so I'll take the typical shortcut of just simply ignoring the subtlety for the purposes of this talk. Okay, so we imagine that we can decompose our system into some number of subsystems, and each of them we can define, for each elementary subsystem we can define entanglement entropy, and also for each composite subsystem we can define entanglement entropy. And so we have a large number of these independent entanglement entropies, which we can now organize into what we call an entropy vector that lives in entropy space, which is the arena which we'll work at, that allows us to start discussing this entanglement structure. Okay, so for example, for 3 parties, this would be the entropy vector, and in general, it's a huge space. It's exponentially large in the number of parties, and so to really probe it at large, the most refined partition, we need some clever ideas. Okay, but this is precisely a limit that we would be most interested in considering, because after all, the bulk is most suggestive of, might be best characterized as the most refined partition of the system. Okay, so now the set of entanglement entropies in this forming the entropy vector has a very rich structure. Okay, you can't have anything. It's highly constrained by relations between these entanglement entropies of the various subsystems. So, for example, a combined entanglement entropy of a composite subsystem cannot exceed the individual entanglement entropies. That's known as the subadditivity, and holds universally for any allowed bipartition of any state in any quantum system. It can be recast as a positivity of mutual information, which simply states that the amount of correlation between the two subsystems A and B is non-negative. Now, a more refined relation is the strong subadditivity, which is simply the positivity of a conditional mutual information, or more intuitively phrased as the sort of monotonicity of the mutual information under inclusion. And well, in general, the more subpartitions of the system you have, the more such constraints one has. But well, depending on what type of system you have. And our task in this talk is to try to determine or figure out a procedure to determine the full set of such thing in the context of holography. Okay. So the set of all physically allowed states in it describes or delineates an entropy cone, a quantum entropy cone, which is a convex cone in an entropy space. And you can think of it in two sort of complementary ways. One is as a convex hull of so-called extreme rays. So any entropy vector must be described as a positive combination of the entropy vectors associated with these extreme rays, or as the intersection of the half spaces given by these entropy inequalities. And so if you have finitely many such linear inequalities, that describes a polyhedron. Okay, and in the context of holography, this has been phrased as the holographic entropy cone a few years ago in this paper. All right. So let me first sort of give you a few results and then tell you how we go about confirming this and generating them. All right, so of course, the set of all, the set of geometric states in some holographic CFT is certainly a proper subset of the set of all quantum states. But just knowing entanglement entropies of some coarse partitioning is a very coarse characterization of the system. And so in fact, it turns out that if you have only two subpartitions, then the quantum entropy cone is actually the same as the holographic entropy cone, and it's just described by the subadditivity along with its cousins under purifications. By purification, I mean observing that the entanglement entropy in a pure state of a given system is the same as the entanglement entropy of its complement, and then allowing yourself to relabel the subsystems. Okay, so these Aracheli inequalities along with the subadditivity form this entropy cone. But for finer partition, the holographic entropy cone is now a proper subset of the quantum entropy cone. And so you need further inequalities that are satisfied by geometric states in holography that need not be satisfied in general. Okay, so for n equal to 3, well, first of all, the quantum entropy cone is, well, it still has these subadditivities. Now there's more of them because you can have various uplifts and permutations that are independent. So there's 6 of these. And there's also 6 of these strong subadditivities. So this, by the way, is not we don't see the radial direction of the cone here. This is just a 3-dimensional slice of the 7-dimensional space. Okay, so that's the quantum entropy cone. The holographic one has all these strong subadditivities chopped off by a new holographic inequality, namely the monogamy of mutual information, which, so this is what we have seen. Here is the monogamy of mutual information, which can be rephrased as a negativity of the tripartite information, or more suggestively as superadditivity of the mutual information. So if you had only quantum entanglement subject to the monogamy property, well then this would be guaranteed. And it's tantalizing to see that it actually holds for all geometric states in the context of holography, which in fact, is very easy. Well, the proof of that using extremal surfaces is almost identical to the proof of strong subadditivity, despite this difference. But I should remark for the aficionados here that if you use the bit thread reformulation of the entanglement entropy, then you do see a substantial difference between these two. And in fact, one can see that the monogamy of mutual information is actually much more deeply rooted in bulk locality than strong subadditivity. Okay, so this was the result for n equal to 3. For four or more partitions, the quantum entropy cone is already not known. And in fact, it might be delineated by infinitely many inequalities. And so this is a very important open problem just from the quantum information science perspective. On the other hand, the holographic entropy cone is still quite simple for 4 parties. It still consists just of the various uplifts and incarnations of the subadditivity and monogamy of mutual information, which now gives 20 independent inequalities. Now, the first place where you get something new is the 5-party holographic entropy cone that has 5 further inequalities that were first specified in this paper and then proved to be complete set in this paper that came out just this spring. So if you're curious what these look like, if I have hyper-compact packaging of them, you can, and very, very compact shorthand, you can fit all of them on a page. In fact, I have written 3 versions of each inequality in different representations, different bases for the entropy space, as you will. It turns out that if you base it on either the multipartite informations or perfect tensors, they perform much more convenient representation than the standard entanglement entropy one. Anyway, so there are these 5 actually separate orbits. Again, the actual inequalities, which are related by relabeling, there are many more of. So we have 372 facets, meaning inequalities that delineate the cone, and thousands of extreme rays. For 6 party, we still don't know the cone completely. We know there are at least 8 further orbits. So now we have tens of thousands of facets and extreme rays, but this is still work in progress. Okay, so now that I have indicated what's known so far, let me go back to specify how we are going about finding these things. Okay, so the strategy, first of all, is to enlarge the quantities of interest from inequalities to all interesting information quantities, which are objects like the mutual information, tripartite information, and so forth. So in general, there's just some linear combination of the entanglement entropies of all the subsystems. And their positivity then gives the inequality, but they're interesting objects which are not necessarily positive. So, for example, the tripartite information is not sign-definite for generic quantum states, but nevertheless, it's a very useful quantity even in that broader context, for example, for diagnosing topological phases and so forth. Okay, so we want to find all interesting information quantities. What I mean by interesting is, well, if you think that they capture some sort of a correlation, we want ones that are able to vanish for some states that don't have that correlation. And we also want them to be independent of all the others. Okay, so we call such a criteria primitive, and we want to describe all such primitive information quantities, which can be associated with each of them can be associated with a hyperplane in the entropy space by simply describing them in the equation of this quantity vanishing. The full set of such primitive information quantities then gives us what we dub the holographic hyperplane, is described by a hyperplane arrangement, codimension 1 hyperplanes in the entropy space, which is actually a rich subject in mathematics, so we can take a lot of mileage from that branch of mathematics. Okay, so that was the first step. The second step now is to really utilize holography. Okay, and well, let me just remind you the prescription for holographic entanglement entropy, which was first formulated by Ryu and Takeyanagi in static context and then covariantized by us more generally, is tells you that the entanglement entropy of a spatial region in a CFT on the boundary is given by quarter of the area in Planck units of extremal surface that's homologous to that boundary region. And often it turns out that there are multiple such candidate extremal surfaces homologous to this region. So out of the whole collection of them, you take the one with the least area. Okay, so that's the prescription. And now the minimality here is actually crucial for our program because it allows for phase transitions in these surfaces. Okay, so if you say imagine a composite system like so, if you separate these regions sufficiently, the entanglement entropy of the composite system is given by the entanglement entropies of the individual ones. But if you bring them close enough together, then this surface in the same homology class actually has smaller area than the collection of these two. And so now you have a different surface. And this will be the key to our constructions. To motivate why that will be the key, let me observe one more aspect, which is that, well, because these surfaces reach all the way up to the boundary, from the holographic standpoint, the entropy is infinite because of this IR divergence. From the CFT standpoint, the entropy is infinite because of the UV divergence. And so, in fact, it turns out that there is no point in the entropy space where you can actually localize a state, an entropy vector for a state in a CFT, because all of the entropies diverge. Now you might say that, well, let's just introduce some cutoff to get it to finite point, but then it's cutoff dependent, and moreover, it's also, you can't even localize it projectively on the celestial sphere, because by changing the spatial dependence of the cutoff, you can change the angles, the ratios between the entanglement entropies. On the other hand, the information quantities can vanish independently of the cutoff. Like here, the mutual information is just identically zero independently of the cutoff because it's the same surface components that get subtracted. And so that suggests that we should deal with these hyperplanes, with these extremal surfaces, and never talk about the areas themselves. And so we'll step back from entanglement entropy to what we call proto-entropy, namely these extremal surfaces, and deal at the level of formal combinations of these extremal surfaces. Okay, so now, just to recap, we want to use these proto-entropies to find the hyperplane arrangement corresponding to all primitive information quantities in holography. Okay, so what we want to do is now scan over classes of configurations of regions on the boundary that would give an information quantity which vanishes, whereas all the other ones in this class wouldn't vanish for that configuration. So for example, this one has all the mutual informations, pairwise mutual informations between A, B, and C, non-zero, in fact infinite here, but the tripartite information is zero. So this would be a generating configuration for the tripartite information. Okay, so you can do this for all the other information quantities. And in fact, now we have abstracted the problem from a geometric one to purely algebraic one. It doesn't matter what sort of shape these are, what state we're in, and so forth. It's just the classes that matter, which HRT surfaces are evoked in these composite subsystems and which are not. Okay, so that's the crux. And so if you implement this program, you get this full holographic entropy arrangement. And now once we obtain such things, we want to go back to our initial problem of finding the polyhedron. The holographic entropy polyhedron is the subset of the information quantities which are sign definite. And so we want to first check out all the ones that are manifestly not sign definite, which we find by evaluating them on separate configurations for which they take different signs. And then for the remaining ones, ideally we want to constructively prove all of them to actually get the full polyhedron. And then once we get the these inequalities, we can then obtain the extremal rays if we want to characterize the entropy cone that way. Okay, so what did we find by following this strategy? So there are no new, even sign-indefinite information quantities for 2 or 3 parties, but there are new ones for 4 and more parties. So for 4 parties, there are 4 new sign-indefinite information quantities, and many for 5 parties. There also, we identified 2 new infinite families of information quantities. One is for, well, it's useful to classify our boundary region configurations by sort of how many levels they get enveloped. So for the simple ones that don't have any enveloping, just disjoint regions which are all simply connected to the to the boundary or to sort of the exterior, we have proved that the only new information quantities we can get are these multipartite informations that are defined in this way for any n. Now, if you have simple singly enveloped regions, you can get this other type of infinite family of quantities, but presumably you can get many more, which we haven't yet explored. Okay, so we get a bunch of these. All right, so I'm now left with 3 minutes, so let me summarize the key points. Okay, so the use of proto-entropies rather than entanglement entropies themselves is quite manifest in this approach, because we never have to worry about any cutoffs or anything like that. And talking about the entanglement structure, localizing a given state in the entropy space on a hyperplane, or perhaps on intersections, higher codimension intersections of hyperplanes, as opposed to trying to localize it at the point, is a very useful method, useful constructively for finding a bunch of these new information quantities. And once we have found those in the context of holography, you may well imagine that now their utility pours beyond holography. They could be interesting information quantities even in the broader quantum mechanical context. The logic of our construction was independent of the number of partitions. We automatically avoided generating sort of redundant relations by this requirement of primitivity. And so, well, we can now go and sort of implement this. It turns out that actually the sieve that we use to rule out the sign, or to identify the sign-indefinite information quantity seems to be much more powerful than we expected. And in fact, you can utilize it even without inputting in candidate inequality to just recover them at the end by basically requiring that the coefficients in this entropy, in this information quantity, have to be such that they don't give you opposite signs on specific judiciously selected set of configurations. And of course, we have been dealing with extremal surfaces, so we don't care about whether the configuration was static or not. And so that leads us to conjecture that the RT cone that's based only on in the static context is indeed the same as the HRT cone, which is the full time-dependent construct. All right, so looking ahead, so we have all these new information quantities and even inequalities, which grows quite a bit with the more refined we make our system. Okay, so where do we go next? How do we make sense of them? I have shown you in a table for n equal to 5, and already, okay, I can fit them in a few lines, but already that sounds like an overwhelming thing. So what is the deeper meaning? So that's the focus of our work now, and I don't have the answer for you yet, but I have a few more speculative sort of questions. In particular, what we want to understand is what aspects of holography imply these relations, and would there be non-holographic systems that also would still imply the same relations? Now, what constraints would these inequalities impose on the structure of the density matrices for all these different subregions? And what is the, correspondingly, if you have, for example, just the mutual information arrangement, the extended sub-additivity cone, for now arbitrarily many parties, arbitrarily fine refinement, and then you reduce it down to your chosen number n of parties, can you actually re-obtain even the holographic inequalities just from this information? And we have some initially very intriguing results that it seems that you can go quite a long way in this direction. And in fact, you might expect that something like this might happen because, well, after all, the HRT phase transitions, in fact, are very naturally related to, well, this quantum marginal independence problem, which is the thing that focuses on this question. Okay, but the bottom line question is, well, is there a general physical principle from which all of these inequalities would follow? Okay, thank you.